The cold air, already thin and sharp, carried the acrid scent of kerosene and burned oxidizer. It was 3:45 a.m., and the steppe was a canvas of deep black and brilliant starlight, broken only by the floodlights illuminating the colossal, white and orange cylinder towering over Launch Pad 1. Inside the launch blockhouse, 2 kilometers away, Colonel Vladimir Kelemai, the irascible chief designer of the OKB-52 Bureau, did not look at the clock. He looked at the face of his counterpart, Vasily Mishin, chief of the mighty OKB-1, the legendary design bureau founded by the late Sergei Korolev. The tension between the two men was a palpable, corrosive presence that had outlived even the great Korolev himself. Mishin was here to oversee the final, nerve-wracking preparations for the launch of a Soyuz 7K T capsule bound for the Salyut 2 space station. This was the steady, incremental path, the Soviet method of proven, crude capsules and modular stations. Kelemai, however, had come for an altogether different spectacle, and his eyes, cold and calculating, held a glint of barely suppressed triumph. A phone rang on a side table. Mishin picked it up, his face tightening as he listened. It was a scramble message from the TSNMASH, Central Research Institute for Machine Building, in Moscow. The message was not about the Soyuz. It was about them. They have made their announcement, Vasily, Kelemai stated, leaning back in his worn leather chair, hands steepled under his chin. He hadn't needed the call to know. His network of agents and political liaisons was as extensive as his rocket designs. The Americans, they call it the Space Transportation System, STS. He rolled the acronym off his tongue like a bad taste. Mishin hung up the receiver with a barely perceptible thud. The Shuttle, a manned bomber dressed up as a logistics vehicle. He scoffed, echoing the standard, pre-approved party line from Pravda and Izveshtia's editorials. It is a financial sinkhole, Vladimir, an impractical boondoggle, a propaganda stunt for the bankrupt NASA program. Of course, it is, Kelemai replied, his voice dangerously smooth. But Vasily, we both know that such pronouncements are for the peasants and the party ideologues. The engineers, the KGB analysts, and the military planners, they see what it really is. He paused, letting his gaze sweep over the wall maps detailing the orbital tracks of American spy satellites. It is a reusable orbital delivery system, Kelemai continued, his voice dropping to a conspiratorial whisper only the two of them could hear over the low hum of the blockhouse's air filtration system. It could put a massive payload into a polar orbit, deploy a military satellite, and return the crew and equipment to be ready again in weeks, not months. Its potential to shift the military strategic balance of power is unsettling. The American announcement on this day in 1972 was the official beginning of the Space Shuttle program. For the Kremlin and the Soviet Military Command, the details of the vehicle, its large delta wing, the cavernous cargo bay, the vertical launch system utilizing external tanks and powerful solid rocket boosters, were not merely engineering curiosities. They represented a fundamental, terrifying paradigm shift. In the Soviet Union's carefully planned, step-by-step space program, where every new component had been tested on a smaller, dedicated vehicle, the Americans were attempting to build a system that was simultaneously an ICBM-class heavy lifter, a maneuverable spacecraft, and a precision glider. The party line for external consumption would be one of derision and confidence in their own proven, expendable rockets like the Proton and Vostok/Soyuz series. But in the deep, secure bunker 200 meters beneath them, the Central Committee's Special Design Bureau, SKB, was already drafting the first tentative intelligence briefs on the American design. Kelemai's presence was no accident. His OKB-52 was known for its massive, powerful, and often controversial designs. The UR-100 and UR-500 Proton rockets were his creations, brute force incarnate. He had already toyed with the concept of a reusable crew capsule that would land horizontally, like an aircraft. Now, the Americans' shuttle presented an irresistible challenge, a chance to outmaneuver Mishin's traditionalist approach and cement his own legacy. As the launch countdown ticked down toward T-minus 5 minutes, the air filled with the rising shriek of the R-7 rocket's turbopumps spooling up. Miss Hin watched the launch monitor, his eyes fixed on the telemetry data. Kelemai, however, was already looking beyond the orange flames that would soon engulf the launch pad. He was looking at drawings he'd secretly acquired, crude photocopies of NASA concept art, smuggled out of Houston and Washington via circuitous routes. He saw not a flawed American project, but a necessary, terrifying blueprint. The Soviet Union, he knew with absolute certainty, could not afford to allow the United States to possess a reusable space-based weapons platform that they themselves did not. The technological gap, however mocked in the papers, was too strategically profound. The quiet race to copy the American machine, bolt for bolt, had just begun. The pressure began to mount immediately after the American announcement. In Moscow, the intelligence reports on the space shuttle, initially dismissed by the party leadership as capitalist excess, were now landing directly on the desk of Dmitry Ustinov, the powerful secretary of the Central Committee in charge of the Soviet defense industry. Ustinov, a pragmatist with a deep distrust of American military intentions, didn't care about the engineering elegance. He cared about payload capacity and orbital maneuverability for weapons deployment. The possibility of the U.S. utilizing the shuttle to snatch Soviet reconnaissance satellites from low Earth orbit, a capability NASA openly, if vaguely, hinted at, was a terrifying prospect for the Strategic Missile Forces, RVSN. By early 1973, a series of urgent, highly classified decrees from the Council of Ministers began circulating through the Soviet defense industrial complex. The first, and most critical, was the mandate to develop a Soviet reusable space system to counter the American threat. The underlying assumption, driven by worst-case scenario military planning, was that the American shuttle was primarily a strategic bomber capable of placing nuclear warheads in orbit or acting as an orbital interceptor. The only acceptable response was a mirror image. The initial design competition was immediately a brutal affair, primarily pitting the two established giants against each other. Vasily Mishin's OKB, now Inco Energia, the direct successor to Korolev's Bureau, and Vladimir Kelemai's OKB-52. Mishin's proposal, designated the Zarya Dawn, was conservative and quintessentially Soviet. It proposed a smaller, partially reusable winged spacecraft, launched atop an improved, heavy-lift version of the existing Soyuz rocket. It prioritized simplicity and relied on proven components. It was safe, affordable, and, critically, did not look exactly like the American shuttle. Kelemai, however, presented a more radical and far more politically palatable alternative. His design, the Molniya Lightning, was a close analog to the American approach, a large, winged orbiter launched vertically on a gigantic expendable booster. Kelemai, leveraging his political connections with Ustinov, argued that anything less than a direct counterpart would leave the Soviet Union strategically vulnerable. Why invent a new wheel when the enemy has provided the blueprints? The critical intervention came not from the designers, but from a military political leadership. Ustinov and the Military Industrial Commission, VPK, ultimately rejected both initial concepts, not because of their technical merit, but because neither was heavy-duty enough. They demanded a booster capable of launching two different payloads, a super-heavy lift cargo vehicle and the reusable winged orbiter. They needed a rocket that could compete with and exceed the projected power of the U.S. Saturn V and the new Shuttle external tank/SRB combination. This forced amalgamation of requirements led to the birth of the Buran program in 1974. The name itself reflected the political compromise. NPO Energia, under the new leadership of Valentin Glushko, who had replaced the embattled Mishin, would design the massive Energia heavy-lift launch vehicle, a rocket of unprecedented power. The design and construction of the actual reusable orbiter, the Buran, Snowstorm, or Blizzard, will be entrusted to a new, specialized division within the Ministry of Aviation Industry, MAP, led by the renowned NPO Molniya Bureau under Chief designer Gleb Lozino-Lozinski. Lozino-Lozinski's mandate was simple, brutal, and crystal clear. Replicate the American Space Shuttle orbiter's external dimensions and aerodynamic characteristics as closely as possible. This decision, a profound humiliation for the Soviet engineering tradition which prized indigenous solutions, was driven by three unassailable realities. Aerodynamic replication. The Soviets did not have time to rerun the thousands of wind tunnel tests NASA had conducted to validate the shuttle's unique high-speed, high-angle of attack reentry profile. Copying the dimensions saved years of research. Military necessity. A direct copy ensured that the Soviet vehicle could perform the same suspected military missions, orbital rendezvous, inspection, satellite capture, as the American one, minimizing the strategic gap. Intelligence access. By 1975, Soviet intelligence, primarily the KGB Directorate T, Scientific and Technical Intelligence, had achieved a staggering level of penetration into the U.S. aerospace industry supply chain. The sheer volume of material, from specific heat shield tile compositions to hydraulic system schematics, made replication feasible, if morally objectionable to the engineers. The Buran project began not with original sketches, but with the meticulous centimeter-by-centimeter scaling of stolen NASA technical drawings. The designers at Molniya, facing the impossible timeline and the immense pressure from Ustinov, quietly began to reverse engineer the most complex spacecraft ever conceived. The irony was not lost on them. The party line publicly denounced the shuttle as a fundamentally flawed design, yet the best minds in the Soviet Union were now dedicated to building a perfect replica of that very flaw. The clock was ticking, and the vast industrial might of the USSR was now being redirected toward this single, covert, technological catch-up. The challenge facing Gleb Lozino-Lozinski and his team at NPO Molniya was not simply to build a spaceship. It was to perform a complex feat of reverse engineering under maximum geopolitical pressure. They had to take fragmented, often incomplete, intelligence and turn it into a working vehicle capable of surviving the violence of launch and the searing heat of reentry. The initial task was the most sensitive, synthesizing the American orbiter geometry. Intelligence reports had provided critical data points: the 51-ring operator sweep of the delta wing, the 102-foot length of the fuselage, and the 78-foot wingspan. The key was the aerodynamic shape. For high-speed flight and atmospheric maneuvering, the geometry was the design. Wind tunnel data, acquired through both human agents and sophisticated electronic interception, was meticulously cross-referenced with blueprints. The resulting Soviet orbiter, the Buran, was dimensionally indistinguishable from the Space Shuttle orbiter from the outside. But the differences began immediately beneath the skin. Lozino-Lozinski, acutely aware of the Soviet Union's chronic issues with miniaturization and electronics, made a crucial, defining decision. The Buran would be an unmanned spacecraft. This was a profound engineering divergence. NASA's shuttle was built around the crew. Its three large SSME's Space Shuttle main engines were located in the orbiter's aft, drawing fuel from the enormous external tank, ET. This complex arrangement allowed the engines to be reusable, but added massive weight and complexity to the orbiter's structure, particularly the thrust structure and plumbing. The Soviet Buran complex solved this problem with a characteristic Russian brute force simplicity. Lozino-Lozinski moved all propulsion for launch off the orbiter. Buran had 0 main engines. Instead, the gargantuan Energia heavy lift booster, 4 powerful Zenit boosters strapped to an enormous core stage, would provide all the thrust to orbit. Buran itself carried only small orbital maneuvering engines, the OMS, and attitude control thrusters, similar to a traditional Soyuz. This decision instantly simplified the orbiter's construction, shedding the massive weight and complexity of 3 reusable high-pressure turbopumps, combustion chambers, and miles of cryogenic propellant lines. However, the heat shield remained the greatest vulnerability and the most difficult piece of American technology to replicate. NASA had spent a decade perfecting the reinforced carbon-carbon (RCC) material for the nose cone and wing leading edges, and the complex high-temperature reusable surface insulation (HRSI) tiles for the fuselage. These tiles were a technological marvel, lightweight, able to withstand thousands of degrees Celsius, and remarkably resistant to thermal shock. Soviet scientists, leveraging intelligence on the U.S. tile composition, primarily the use of 99.7% pure silica fiber, developed their own version designated UR1 and UR2. But the manufacturing process was slow, difficult, and prone to cracking. The sheer precision required to bond 38,000 unique, hand-cut tiles to an aluminum airframe was a nightmare of quality control for Soviet industry, which often prioritized quantity over precision. Engineers joked darkly that Buran was not a ship, but a flying ceramic workshop. The internal systems presented another chasm. The American Shuttle relied heavily on state-of-the-art digital fly-by-wire systems, utilizing sophisticated Honeywell and IBM flight computers. Soviet electronics were notoriously bulky and less reliable. Therefore, Buran was equipped with 5 Argon-16 computers, reliable, battle-tested machines developed for missile guidance. But their programming had to be far more robust and automated than the American counterpart, specifically to manage the entire flight profile autonomously. Since Buran was designed to fly without a crew, its automatic landing system had to be perfect, guiding the 70-ton glider from orbital speed to a runway touchdown without human intervention, a capability the American Shuttle possessed only as a backup. The construction took place across hundreds of facilities, including the massive Tushino machine building plant in Moscow and the assembly halls of Baikonur. The sheer scale of the program, involving over 1,200 enterprises and ministries and the mobilization of over 1 million personnel, was a testament to the Soviet commitment. Yet, every week brought new frustrations. Small intelligence leaks were insufficient for precision engineering. The team had the what, the dimensions and the materials list, but often lacked the how, the exact manufacturing tolerances and processes. It was a race against time, a furious scramble to close the technological gap before the first American shuttle, Columbia, even left the launch pad. The success of this massive, secret undertaking would depend entirely on the brute force of Soviet industry and the meticulous, if ethically dubious, groundwork laid by the KGB. The KGB's role in the Buran program was not merely supportive, it was foundational. The organization's first chief director at Foreign Intelligence maintained a specialized branch for scientific and technical intelligence, or S&T, known as Directorate T. By the mid-1970s, the entire U.S. space shuttle program was for Directorate T, the single most critical technological target on Earth, designated as Line X. The intelligence requirements, passed down from the Military Industrial Commission, VPK, to the KGB, read like a detailed, itemized shopping list for a complex American aerospace project. It was a clear admission that indigenous Soviet research, while capable, could not produce the necessary technologies in the required time frame. The list was prioritized, focusing on the 3 areas where the American lead was insurmountable. Thermal protection system, TPS specifically, the exact chemical composition, density, and bonding process for the high-temperature, reusable surface insulation, HRSI tiles. The KGB needed to know the mixture of silica fibers, the precise coating materials, e.g., borosilicate glass, and the tolerance specification for the thousands of gaps between the tiles, which prevented the aluminum airframe from warping during reentry. Digital flight control systems, the complex, fault-tolerant fly-by-wire architecture. The Soviets had strong, albeit bulkier, computer hardware, but the American redundancy and software protocols, the entire concept of multiple computers constantly checking each other to prevent a single point of failure, were an engineering leap they desperately needed to understand. Advanced materials, new high-strength, low-weight alloys, specifically those used in the main engine pumps. Even though Buran didn't use them, the underlying metallurgy was critical, and the specialized hydraulic fluid formulations that could withstand the high temperatures and pressures of the system. The espionage operation became a sprawling, global network. KGB Line X officers, often disguised as trade representatives or academic exchange students, operated out of Soviet embassies and consulates in New York, Houston, and Los Angeles. Proximity to NASA and its prime contractors like Rockwell International and Lockheed was paramount. Their method was not always a classic spy exchange in a darkened park. Often, it was simpler, exploiting the open nature of American academia and corporate culture. A common tactic was the use of open-source acquisition. Documents detailing thermal analysis, aerodynamic stability, and structural loading were sometimes published in professional engineering journals or presented at unclassified conferences. These documents, though sanitized of classified details, contained enough fundamental research to provide the Soviet engineers with critical insights into the American thought process. A paper on a new type of wing-body vortex lift, for example, could confirm years of internal Soviet theorizing on the delta wing's reentry characteristics. More direct methods involved cultivating agents of influence and recruiting engineers and technicians with access to low-level but highly specific blueprints. One critical piece of intelligence was the detailed geometric model of the shuttle's aluminum internal frame, providing the key structural load paths that governed the entire vehicle's design. This was the skeleton onto which everything else was bolted. The geometric replication of the Buran airframe, down to the curve of the fuselage leading into the tail fin, was a direct result of acquiring these structural details. However, the most prized and most elusive secret was the heat shield tile bonding process. Rumors persisted in Moscow that the CIA and FBI, aware of the massive Soviet effort, were engaging in a massive disinformation campaign, feeding intentionally flawed blueprints into the KGB's network. Some Soviet engineers, particularly those struggling with the complex thermal stresses on the Buran's test panels, began to suspect that the very information they had risked their lives and careers to acquire might be subtly poisoned. One engineer at the Ticino machine building plant reportedly delayed the installation of a batch of copied American hydraulic valves, convinced the manufacturing tolerances, meticulously copied from a capture diagram, were just slightly off. The pressure was immense. Success meant saving the Soviet Union from military humiliation. Failure meant a career-ending meeting with a high-ranking party official and the possible collapse of the vehicle and the program. By the late 1970s, the design decisions for Buran were no longer guided purely by physics, but by a chilling, dialectical interplay between stolen American designs and the nagging fear of deliberate deception. The engineers building a copy had to constantly ask themselves, was this design choice dictated by optimal physics or by the American intelligence community? While the team at NPO Molniya struggled with the painstaking replication of the American orbiter, a separate, equally colossal task was underway to create its launch platform. This was the Energia Super Heavy Lift Launch Vehicle, the expendable behemoth designed to fling the 100-ton-plus Buran into orbit. This element, the booster, was the area where Soviet engineering diverged most significantly, and arguably, most successfully from a NASA approach. The Americans had placed the shuttle's three powerful space shuttle main engines, SSMEs, on the orbiter itself, a design choice meant to make those valuable engines reusable. The Soviet engineers, however, recognized that this design placed impossible structural loads on the delicate, winged orbiter and necessitated the use of massive amounts of highly volatile, cryogenic hydrogen fuel in the orbiter's tail. Valentin Glushko, the chief designer of NPO Energia, who now spearheaded the entire booster program, opted for a classic Soviet solution: distribute the power and keep the orbiter simple. Energia would be a parallel-staged rocket, a configuration that provided tremendous flexibility. The core of Energia was a massive, central cryogenic stage powered by four RD-0120 engines. These were advanced, liquid hydrogen/liquid oxygen engines, burning the same high-energy propellants as the American SSMEs. But unlike the SSMEs, they were expendable. they were left to burn up upon reentry. This made them simpler, cheaper, relatively, and far more reliable to manufacture than the complex, reusable American engines. Crucially, strapped to the core were four powerful, reusable, but expendable on this flight, strap-on boosters, utilizing the proven, kerosene-fueled, high-thrust RD-170 engines. The RD-170 was a masterpiece of Soviet engine technology, a cluster of four combustion chambers sharing a single turbopump, making it the most powerful liquid-fuel rocket engine ever flown. This was the brute force component of the Soviet design. The genius of the Energia lay in its versatility, a feature the American Shuttle lacked entirely. Once the Buran orbiter was detached, the Energia rocket could be used independently as a pure heavy-lift vehicle, capable of lofting up to 100 metric tons into low Earth orbit, LEO. This capability, called the Energia Universal Configuration, was a long-coveted dream of the Soviet military for launching massive, classified payloads or future space station modules, a true Saturn V successor. However, the creation of the launch infrastructure for this colossal rocket was a staggering civil engineering feat. The existing launch pads at Baikonur, designed for the R-7 family, Vostok/Soyuz, were entirely inadequate. The Soviets had to construct a brand-new, purpose-built complex, Launch Complex 110, featuring two enormous pads. The assembly process was a logistical nightmare. The massive components, the core stage, the strap-ons, and the fragile Buran orbiter were transported to the assembly building, the MIK, Montazno Ispitatelny Corpus, using gigantic, specially built railcars. The sheer size of the integrated Energia Buran stack, towering over 60 meters, necessitated the construction of an equally large, specialized transporter rector system that dwarfed the systems used for the smaller Proton rocket. This era, the early 1980s, marked the peak of Cold War technological spending for the USSR. Resources were virtually limitless, channeled through the shadowy VPK. Thousands of kilometers of roads were built, new airfields were constructed, including the massive Yubileyny airfield designed specifically for Buran's horizontal landing. And entire new towns were expanded to house the engineers, technicians, and military personnel assigned to the program. The project was simultaneously a statement of national power and a massive drain on the collapsing Soviet economy. When the first full-scale orbiter, Buran 1.01, was officially rolled out in 1984, Western intelligence satellites, primarily the American Keyhole series, captured the images. The shock in Washington was profound. The vehicle was not just similar to the space shuttle. It was its spectral, white and black twin. This visual confirmation solidified the U.S. intelligence community's worst fears. The Soviets had not only countered the shuttle, but had done so through a devastatingly successful espionage campaign. The sheer audacity of the replication, coupled with the immense power of the Energia booster, turned the propaganda tables the Soviets had used years earlier into a terrifying symbol of their industrial and intelligence capability. The public mocking of the shuttle was revealed to be a cynical cover for a billion-ruble theft. Before the Buran could be strapped to the Energia stack for its one-way trip to orbit, and hopefully back, the Soviet engineers needed to master the vehicle's single most complex, non-rocket-powered flight phase, atmospheric flight, and automated landing. A winged vehicle, falling from orbit at Mach 25, then maneuvering through the dense atmosphere to land on a runway, was an aerodynamic challenge unlike anything the Soviet Union had ever faced. NASA relied on its veteran test pilots, like John Young and Robert Crippen, to manually control the shuttle during its first crucial landings, providing invaluable real-time feedback. Since the Buran was designed to fly entirely unmanned, a philosophical and technical difference necessitated by the bulk of Soviet electronics, its automated flight control system had to be flawless from the very first attempt. To validate the airframe's integrity and the critical automated landing software, NPO Molniya developed a crucial piece of hardware. The Buran analog BST-02, later nicknamed OKGLI, Russian for orbital ship, horizontal flying analog. This was a full-scale, flight-capable version of the Buran orbiter, complete with the weight, dimensions, and center of gravity characteristics of the real spacecraft. The key difference was propulsion. The OK-GLI was fitted with 4 non-afterburning L-31 turbojet engines, taken from a Sukhoi fighter jet. Mounted in the tail where the Orbital Maneuvering System, OMS, pods would eventually sit. These jets allowed the analog to take off conventionally, fly to altitude, and then perform simulated landing maneuvers without requiring the constant, expensive, and dangerous airlift launches used by NASA's Enterprise test article. Testing commenced in 1984 from the Zhukovsky airfield near Moscow, overseen by a cadre of elite Soviet test pilots, including the legendary Igor Vok. Their mission was paradoxical: fly an aircraft that was designed not to be flown by humans in order to validate the software that would replace them. Vok and his team, members of the newly formed cosmonaut training group for the Buran program, had to deliberately simulate the dead-stick glide profile of the orbiter. After reaching altitude using the turbojets, the pilots would shut down the engines and glide the massive, delta-winged vehicle down through a complex series of turns and energy dissipation maneuvers. The Buran's aerodynamic profile, copied meticulously from the American Shuttle, provided a significant cross-range capability, the ability to maneuver laterally after reentry to reach a landing site far from the ground track. This was essential for the suspected military missions and required the control surfaces, particularly the split rudder/speed brake and the elevons, to be incredibly powerful and responsive. The test flights focused on 3 main parameters. Low speed handling. How stable was the heavy glider at landing speeds? Around 300 to 350 kilometers per hour. The pilots consistently reported that the Buran was a stable, if heavy, glider, far better behaved than the American Shuttle's early simulations suggested NASA's bird would be. Glide slope control, validating the performance of the hydraulic control systems and the precision of the flight surfaces when transitioning from high-altitude atmospheric entry simulations to the final approach. Automated landing system, ALS, this was the ultimate test. The pilots would fly the OK-GLI to a certain altitude and speed, then engage the Argon, 16 flight computers, and let the machine take control. The ALS, utilizing a ground-based microwave scanning beam system for precision guidance, had to autonomously manage the complex energy profile, flare for landing, and deploy the massive drag chute, all without human input. In total, the OK-GLI analog performed 25 atmospheric test flights. The most stunning achievement was the consistency of the fully automated landings. On multiple occasions, the pilots watched, hands hovering near the controls, as the Buran analog executed perfect centerline landings. This ability to land a winged spacecraft autonomously represented a technical triumph that eclipsed even some of the initial American capabilities, which prioritized manual control. The training flights were not without incident. The vehicle, being essentially a brick with wings at low speed, required tremendous skill to handle manually, reinforcing the wisdom of Lozinski's decision to rely on automation. The pilots, though crucial for data gathering, were validating a system designed to make them redundant. The success of the OK-GLI tests cemented the confidence of the Soviet military and party leadership. They had not only copied the external form of the American challenge, but had engineered a potentially more reliable, if less flexible, operational profile. The stage was now set for the ultimate flight of the real orbiter, Buran 1.01, at the height of a crumbling empire. The year was 1988. The Cold War, while officially thawing under the policies of glasnost and perestroika championed by Mikhail Gorbachev, was still very much a technological battleground. The United States had successfully launched and operated the Space Shuttle fleet for 7 years, demonstrating its operational potential, though punctuated by the catastrophic loss of Challenger in 1986. For the Soviet Union, the need to demonstrate the successful launch of Buran had morphed from a military necessity into a crucial matter of prestige and ideological survival. At the massive launch complex 110 at Baikonur, The preparations for the first uncrewed flight of the Energia-Buran complex were a study in frantic, centralized chaos. The sheer scale of the assembled stack, the four metallic gray Zenit boosters, the white cryogenic core stage, and the stark white and black Buran orbiter bolted rigidly to the side, was breathtaking. This was the most powerful launch vehicle ever assembled by the USSR. Chief designer Gleb Lozino-Lozinski was under intense scrutiny. His engineers had successfully navigated the technological hurdles, but the political environment was a crucible. The first launch attempt in October 1988 was scrubbed just 51 seconds before ignition. The massive hydraulic swing arm, designed to provide access and support to the orbiter's delicate systems, failed to retract fully and lock away. It was a minor technical fault, magnified into a crisis by the geopolitical spotlight. For the American intelligence community, the upcoming launch was an unparalleled event. Reconnaissance satellites were redirected to provide continuous coverage of Launch Complex 110. Analysts in Washington and Houston studied every piece of imagery, seeking confirmation of their initial intelligence. Was the Buran truly a near-perfect replica? And more importantly, could the Soviets successfully manage the incredible complexity of launching it? The American team was particularly skeptical of the Soviet ability to launch and land the winged vehicle automatically, given the inherent unpredictability of hypersonic reentry physics. The technical hurdles during the final weeks were immense. The Buran orbiter, designated 1.01, had approximately 38,600 unique ceramic tiles. The final process of gap filling, waterproofing, and tile inspection was agonizingly slow. Unlike the American system, where a team of technicians constantly checked the tiles, the Soviet process suffered from systemic quality control issues inherent to a command economy. Engineers often had to improvise solutions for minor defects, leading to internal debates over whether the integrity of the heat shield was truly robust enough for the thermal extremes of reentry. The Energia booster itself presented its own challenges. The powerful RD-0120 hydrogen engines and the four RD-170 kerosene boosters were designed to deliver a staggering 3,500 tons of thrust at liftoff. The control software had to manage the complex, asymmetrical thrust profile caused by the Buran's side-mounted position, a configuration that essentially meant the rocket was being pushed by a powerful, off-center force throughout the ascent. Despite the technical complexity, the political pressure from the Central Committee was non-negotiable. The launch window had to be hit. November 15, 1988, was set as the new date. In the blockhouse on the morning of the launch, the atmosphere was a mix of bone-numbing cold and nervous energy. The clock ticked past 6 a.m. local time. Glushko and Lozino-Lozinski stood side by side, united in their anxiety over the culmination of nearly 15 years of frantic work and espionage. The primary mission objective was simple: launch the orbiter, perform 2 full orbits, validate all systems, especially the automated flight controls, and perform a fully automated landing at the Yubileyny airfield. If successful, it would prove that the Soviet Union could match the American capability and, in a critical sense, exceed it by demonstrating full autonomy. If it failed, the massive investment would be written off as the ultimate Cold War folly. The final decision to proceed rested on the shoulders of the elderly, exhausted chief designers, who knew that this launch represented one of the final, desperate attempts of the old Soviet system to assert its technological supremacy. The weight of the failing empire was resting on the 4 nozzles of the RD-0120 engines. November 15, 1988. 6 a.m. Baikonur Cosmodrome. The launch command, delivered over the loudspeaker with a chilling formality, was given. Zazigany. Ignition. There was no immediate visible change, only the deep, subterranean rumble that preceded every major Soviet launch. Then, with a sound that seemed to tear the very air, the 4 monstrous RD-170 engines on the strap-on boosters roared to life. Kerosene and liquid oxygen, compressed and burned with unimaginable force, erupted in columns of brilliant orange-white flame, bathing Launch Complex 110 in a light brighter than the desert sun. A split second later, the four central RD-0120 engines of the core stage ignited with the cleaner, sharper flame of burning liquid hydrogen. For a moment, the immense Energia minus Buran stack hung suspended, held down by massive clamps, trembling under the stress of 3,500 tons of thrust. The engineers in the bunker, many of whom had been working on this single colossal project for over a decade, watched the telemetry screens with bated breath. This initial, asymmetrical thrust phase was the most dangerous. The off-center load of the Buran orbiter, strapped only to the core, meant the rocket was intrinsically unstable, requiring immediate, precise control input. At T-0, the clamps released. Slowly, majestically, the complex began to rise. The ascent was thunderous, an unparalleled display of Soviet brute force capability. The four RD-170 engines, with their combined 8 combustion chambers, consumed fuel at an alarming rate, punching the heavy vehicle through the dense lower atmosphere. The control system, managed by the onboard TSVM, 10 computers, worked overtime, compensating for the wind shear and the inherent thrust vector instability. On the tracking screens in the blockhouse, the trajectory line remained rock steady. 2 minutes and 32 seconds into the flight, an altitude of approximately 50 kilometers, the 4 external Zenit strap-on boosters depleted their fuel. With a series of carefully timed pyrotechnic bursts, they peeled away from the core stage, falling back toward the vast, uninhabited Kazakh steppe. The core stage, powered by the 4 cryogenic RD-0120 engines, continued to burn, pushing the now lighter complex toward orbital velocity. This was the first successful launch of the colossal Energia heavy-lift vehicle, a testament to Valentin Glushko's engineering genius, wholly separate from the Buran orbiter. Its success immediately validated the Soviet military's dream of a 100-ton cargo capability. At 460 seconds, just under 8 minutes, the core stage engines shut down. The Energia core, having done its work, detached and began its uncontrolled ballistic descent. For the first time, the Buran 1.01 orbiter was a free spacecraft. The onboard Argon 16 flight computers immediately took over, activating the smaller, hypergolic orbital maneuvering systems, OMS, engines, which are designed to push the spacecraft into its final, precise to-orbit trajectory. The computers also checked the critical systems, power generation, cooling loops, and, most importantly, the thermal protection system, TPS. Sensors embedded beneath the 38,600 silica tiles were confirming that all was nominal. In orbit, the uncrewed orbiter was now performing the very maneuvers the American military had feared. It was a winged, highly maneuverable platform with a massive, empty payload bay, a direct mirror of the capability the Pentagon had sought in the early days of the space shuttle. Western tracking stations, including NORAD, watched in disbelief. The Soviets had not just built a shuttle-like vehicle. They had built a working, high-performance orbiter launched on a rocket of unparalleled power. The visual confirmation of its flawless ascent, though captured only by grainy satellite imagery and internal Soviet tracking film, was a stunning geopolitical announcement. Moscow had copied the Americans' most complex vehicle, and it had done so in the uncrewed configuration that made it an even more potent military prospect. The stage was now set for the final act, the landing, which had to be performed by the machine alone. The Buran 1.01 orbiter settled into its planned orbital trajectory, completing its first flawless loop around the Earth. The entire duration of the two-orbit mission was just 206 minutes. In the control center at Baikonur, the sense of victory was palpable, but muted by the lingering, paralyzing fear of the final, crucial phase, re-entry and landing. No winged spacecraft of this size had ever performed a fully automated atmospheric flight and runway landing before. At the beginning of the second orbit, over the Pacific Ocean, the Argon 16 flight computers received the final sequence command. The Buran's OMS engines fired in a precise 3-minute deorbit burn, slowing the vehicle and setting it on its path toward the atmosphere, targeting the newly constructed Yubilani airfield landing strip. As the spacecraft plunged toward the atmosphere, the external skin began to glow with the infernal heat of atmospheric friction. At Mach 25, the temperatures on the nose cone and wing leading edges, protected by the Soviet-made reinforced carbon-carbon RCC analogs, neared 1650 ring operator C. The sensors beneath the tens of thousands of silica tiles, copied and manufactured under such intense pressure, were relaying critical data. The TPS was holding. The trajectory was perfect, dictated by the onboard systems reacting to minute atmospheric drag fluctuations. Crucially, the Buran executed a series of calculated banks and S-curves, necessary to bleed off speed and energy while maintaining the required cross-range capability to reach the precise landing point thousands of kilometers away from the reentry point. This complex, high-G maneuverability had been a primary military driver for the entire project. As the orbiter dropped below Mach 5, the flight profile transitioned from the physics of spacecraft to the aerodynamics of a heavy, unpowered glider. The air density became high enough for the rudder and elevons to become effective. The Buran, now a massive 70-ton unpowered glider, began its high-speed dive toward the steppe. At the Yubilani airfield, the weather was rapidly deteriorating. The predicted calm conditions had given way to rain squalls and a brutal, unexpected crosswind gusting at over 60 kilometers per hour, far exceeding the published maximum crosswind limit for the American Space Shuttle manual landing procedure. This unforeseen meteorological challenge was the ultimate test of the Soviet automation. A human pilot would have struggled intensely. The computer had to compensate flawlessly. The ground-based microwave scanning beam landing system, MSBLS, locked onto the descending orbiter, providing the precision guidance data to the Argon-16 flight computers. At a height of 15 kilometers, the computer took full, absolute control for the final approach. Watching from the control tower, chief designer Lozino Lozinski held his breath. He had designed the machine, but the machine had to save itself. The Buran banked steeply, adjusting its glide path, its control surfaces constantly twitching to compensate for the violent crosswinds. It was a mechanical ghost ship, flying a perfect, textbook approach profile through weather conditions that should have forced an abort. At 300 meters, the orbiter began the final pre-flare maneuver, leveling off slightly to slow its descent rate. At 15 meters, the computer executed a delicate flare, pulling the nose up to arrest the vertical speed, trading momentum for a gentle touchdown. Precisely at 9:42 a.m. Moscow time, Buran 1.01 contacted the asphalt of the runway. There was a faint puff of smoke from the main landing gear tires, followed by the deployment of a massive drag chute from the tail, perfectly centered and timed. The touchdown velocity was just over 300 kilometers per hour. The orbiter rolled to a complete stop exactly at the calculated midpoint of the 5-kilometer runway. The success was immediate, total, and stunningly complete. Buran had performed a perfect, fully automated landing in weather conditions that were borderline catastrophic. Engineers rushed to the vehicle, finding that the external damage was minimal. Only 5 of the 38,600 heat tiles were reported missing or damaged, an astonishing testament to the quality of the reverse-engineered TPS and the precision of the reentry trajectory. This single, uncrewed flight was a massive, if fleeting, propaganda victory. The Soviet Union had proven that it possessed a vehicle that could perform the exact strategic mission of the American shuttle, and it had demonstrated a superior level of automation in the most critical phase of the mission. The engineers had copied the American blueprint, but in doing so, they had produced a machine that, in key areas of structural simplification, no main engines, and automation, arguably surpassed its copied counterpart. The perfect autonomous flight of Buran 1.01 sent seismic shockwaves through Washington and NASA headquarters in Houston. The immediate response from the West was a mixture of stunned admiration and deep concern. The CIA and NORAD analysts, who had monitored the launch and descent meticulously, were forced to reckon with two critical, undeniable facts. Replication was successful. The Soviets had, against all predictions of internal technical limitations, successfully replicated the most complex aerospace vehicle ever built. The visual similarity was total, confirming the success of the KGB's Directorate T espionage campaign. Automation superiority. The fully automated landing demonstrated a level of computerized flight control autonomy that the American shuttle system, which always relied on crew intervention for landing, did not possess. This capability immediately elevated the military threat profile of the Buran, as it could theoretically be launched from any remote Soviet base and returned without risking a high-value pilot. In the aftermath, Western analysts studied the Soviet press releases and limited film footage, attempting to understand the design philosophies behind the copy. The core realization was the difference in engine placement. NASA's engineers had chosen reusability for the main engines, placing them on the orbiter. The Soviets, prioritizing Buran's structural integrity and overall system reliability, had put all the launch thrust on the expendable Energia booster. They built a better launcher and a simpler orbiter, remarked one senior NASA official privately. The Energia heavy lift capability, demonstrated independently for the first time, was an even greater long-term military concern than the winged orbiter. The Energia had the power to orbit enormous space-based weapons platforms or strategic command centers, fulfilling the original Soviet military requirement that catalyzed the entire program. However, beneath the public triumph, the Soviet engineers were brutally honest about the internal flaws of the copied system. While the Buran flew perfectly once, the path to that single flight had exposed the systemic weaknesses of the Soviet industrial complex. The heat tile crisis. Despite the perfect performance on the maiden flight, the manufacture and installation of the Buran's 38,600 tiles was still a slow, agonizing process. The tiles required a level of microscopic precision and purity that was difficult to maintain across hundreds of disparate, often poorly equipped factories. The system was costly, manually intensive, and ultimately not scalable for a fleet of orbiters, which was the original plan. Electronics bulk. While the Argon-16 computers were robust, they were physically massive compared to their miniaturized American counterparts. The sheer bulk of Soviet-era digital electronics meant that the Buran had a lower effective payload capacity than the American shuttle, despite being dimensionally similar. The reliance on sheer volume of wiring and heavy, power-hungry components was a significant disadvantage for a vehicle where every kilogram counted. Operational cost and time. The entire Energia minus Buran system was astronomically expensive. The Energia booster, though reusable in principle, was primarily intended to be expendable for the Buran mission profile, making the cost per launch far higher than a traditional Soviet expendable rocket like the Proton. The American justification for the shuttle, that it would lower launch costs, had proven false in the U.S. system, and it was certainly false in the Soviet imitation. The long turnaround time for assembling and checking the complex components at Baikonur meant that the promised rapid reusability was an operational fantasy. Furthermore, the KGB's fears of disinformation were partially realized, though not in the way they expected. While the Buran design wasn't based on a rejected NASA concept, the constant fear of sabotage had caused significant delays and second-guessing among the Soviet designers, draining precious time and resources. In a final analysis, Buran was not a better machine because it was a copy. It was a testament to the immense political will and brute force engineering capability of a dying superpower. It was the ultimate statement of technological parity achieved by industrial espionage, a machine built not for its utility, but for the singular purpose of denying the enemy a monopoly on a critical military platform. The price of that statement, however, was about to be reckoned by an economy on the brink of collapse. The perfect flight of Buran on November 15, 1988, proved to be the project's technological zenith and its political swan song. Less than 3 months after the triumph, the financial and systemic rut plaguing the Soviet Union began to metastasize, directly impacting the sprawling Energia-Buran enterprise. The cost of a single Buran flight was staggering, consuming resources desperately needed elsewhere in the failing Soviet economy. The entire program was estimated to have cost over 20 billion rubles, a figure comparable to the cost of the entire Soviet manned space effort to that point. Unlike the expendable Soyuz rockets, which were cheap to produce and flew frequent missions, the Buran system required the constant, high-precision manufacturing of specialized, non-standard components, including the massive Energia core stage and the fragile, unique heat shield tiles. Mikhail Gorbachev's reform policies, while aimed at saving the USSR, inadvertently created the conditions for the program's paralysis. As the central authority of the Military-Industrial Commission, VPK, weakened, the flow of unlimited funds and priority materials that had shielded the project for 15 years began to dry up. The network of over 1,200 enterprises involved in the program, accustomed to following top-down directives regardless of economic sense, suddenly faced budget cuts and bureaucratic inertia. The second orbiter, Tychka, Little Bird, was nearing completion and was slated for a crewed test flight to the Mir space station. However, its completion schedule slipped repeatedly. Factories across the country, which had previously dropped all other work to produce Buran components, now prioritized paying contracts and local needs over the prestige project. Deliveries of key items, from high-strength metal alloys for the airframe to sophisticated avionics components, slowed to a crawl. The entire assembly line at the Tashino machine building plant was effectively mothballed by 1990. The strategic rationale, the original driver of the espionage and massive spending, also evaporated. The Buran was born out of fear that the American space shuttle was a space bomber. By the late 1980s, the U.S. had largely shifted the military focus of its shuttle program, relying less on its unique capabilities and more on standardized, expendable rockets for critical defense payloads. Furthermore, the Soviet Union's own intelligence agencies concluded what its economists already knew. The shuttle design, though technically brilliant, was fundamentally inefficient for routine access to space. In 1990, the Energia-Buran program was formally placed on conservation status, a euphemism for indefinite suspension. The decision was not driven by engineering failure, but by economic reality. The empire could no longer afford its most visible symbol of technological parity. The subsequent collapse of the Soviet Union in December 1991 turned conservation into cancellation. The program, distributed across the now independent republics of Russia, Ukraine, and Kazakhstan, was politically and structurally impossible to sustain. The newly formed Russian space agency, Roscosmos, inherited the hardware, but not the budget or the political backing required for such a massive program. The completed Buran 1.01 orbiter, the one that had flown its perfect mission, was stored disassembled at its home base, the MIK, Montazno-Ispitatelny Korpus, at Baikonur, which now lay in the sovereign nation of Kazakhstan. It was intended to be the jewel in the crown of Soviet space achievement, but it became a relic overnight, a monument to a race that was simultaneously won and lost. The two flight-ready Energia heavy-lift boosters, the most powerful rockets ever produced by the Soviets, sat and used, their technology unmatched even by the American fleet. The vast infrastructure built around the program, the complex launch pads and processing facilities, were left derelict and exposed to the harsh desert climate. The legacy of the Buran was transforming from a source of national pride into a painful symbol of Soviet overreach. The very machine built to demonstrate Moscow's enduring power was now a spectral witness to its dramatic demise. The final, ignominious chapter of the Buran program was written not by engineers or cosmonauts, but by neglect and a tragic structural failure. The perfect orbiter Buran 1.01 remained stored inside the cavernous, high-bay assembly building, MIK, at Baikonur Cosmodrome, now under the tenuous control of the newly independent government of Kazakhstan. For over a decade, the vehicle sat in limbo. Various proposals for its reuse, ranging from a Russian-Kazakh joint venture to a high-profile sale to a Western museum, were floated, but none materialized. It was too massive, too complex, and too expensive to move or restore. The orbiter was parked alongside its powerful and used launch vehicle, the second flight-ready Energia booster. They represented a combined technological capability that was unmatched globally, yet entirely devoid of a mission. The end came with a sudden, devastating finality on May 12, 2002. The MIK building, vast and poorly maintained after years of systemic neglect and exposure to the severe Kazakh climate, was structurally compromised. A massive section of the high bay's roof, weakened by heavy rain and corrosion, collapsed inward. The falling debris, tons of steel and concrete, crushed the Buran 1.01 orbiter and the flight-ready Energia booster, reducing the twin symbols of Soviet technological rivalry to mangled wreckage. The destruction was complete. The Buran, the perfect copy that had achieved a flawless automated flight, was physically eliminated. The event was not just an industrial accident. It was a potent metaphor for the final collapse of the Soviet state's ambitions. The technological might achieved through massive investment and successful espionage was ultimately undone by the decay of the very infrastructure that supported it. Today, the legacy of Buran is complex, residing primarily in the knowledge it generated and the subsequent analysis of its design by Western engineers. The verdict of the West. Western analysts who gained access to the program's internal data after the Cold War often concluded that, ironically, the Buran program was strategically valuable not for what it copied, but for what it forced the Soviets to invent. The RD-170 engine and the Energia booster technology, pure Soviet innovations, remain some of the most powerful and efficient liquid-fueled propulsion systems ever designed. Elements of RD-170 descendants are still used on modern Russian and American rockets, proving that the brute-force Soviet approach to heavy lift was technologically superior to the U.S. solid rocket booster, SRB, concept. The autonomous flight control system was a genuine technological lead, demonstrating that computer-guided landing of a hypersonic glider was achievable without a human crew. The internal contradiction. The Buran project perfectly encapsulated the late Soviet Union's defining contradiction, its ability to mobilize vast resources and execute world-class engineering. The Energia rocket, while simultaneously remaining dependent on Western technology for high-complexity, micro-precision components, the orbiter's TPS and avionics, acquired through industrial theft. The successful replication of the Space Shuttle proved the efficiency of the KGB's Directorate T, yet the very existence of the copy validated the American strategy. The Buran program became the ultimate proof of the maxim it was designed to deny, that the American Space Shuttle, despite its flaws, was a necessary technological leap that forced the Soviet Union into a massive, unsustainable catch-up effort. The Soviets had mocked NASA's shuttle, calling it impractical, but their own, nearly identical, Buran was the definitive multi-billion ruble admission that the military strategic potential of the winged, reusable spaceplane was too terrifying to ignore. It flew once, a ghost ship on a perfect mission, only to be consumed by the dust of the empire that created it. The cost of technological paranoia was paid in full.